Hey everybody, Mr. Murray here, Mr. Murray's Mathland. We're looking at solving systems of equations, but today we're looking at it by using the method called substitution. Prior to this, we had used graphing, which is a great first way to do it. You'd graph both lines and see where they intersect, or if they intersect at all. But you may have run into a problem that you don't always have graph paper in front of you, and it can be a little annoying to try to sketch and be careful without some nice graph paper. And also, what if they intersect, way out at a point like 40 comma 2 or 100 comma negative 50? Or what if they intersect at, fractional values where it's hard to tell exactly where they're intersecting? So there are limits to the graphing is my point. And so we're going to learn one of the algebraic methods today, which is called substitution. So here is when substitution is great to use. Now, substitution can be used on any system. It really can be. But there are times when it's really good to use it. And when it's good to use substitution is when you have, in your two equations, if you have one variable that is already isolated or could be easily isolated. So for example, you see in this second equation, I have x all by itself. I have x equals 3y plus 9. So this is when substitution is great to use. When one variable is isolated or is easy to isolate. So, if you don't have that right off the bat, but it could be easily isolated, you could do this, what we're about to do. So here's the deal. If x in this system is equal to 3y plus 9, I'm going to go to the other equation, the first equation, in this case 5x plus 12y equals 27. And if x is equal to 3y plus 9, x is equal to 3y plus 9. Whoops, I'll just take that away there. If x is equal to 3y plus 9, I'm going to go to the other equation, and where I see x, I'm going to replace it with 3y plus 9. So here's what I'm going to do. 5 and in place of x, and the rest of the equation exactly the same. 5 blank plus 12y equals 27. I'm going to take out that x and replace it with 3y plus 9, because that's what x is equal to. So if I plug that in, now I've made one equation all with the same variable, and that I can solve. Now this is just an equation with y in it, so I'm going to use my distributive property. I'm going to distribute 5 to this and get 15y plus 45 plus 12y equals 27. Right, now I'm just going to use my algebra skills here. Combine my like terms. 15y plus 12y is 27y plus 45 equals 27. And now I'm going to subtract 45 from each side. Right, this is the part where it's like autopilot. 27 minus 45, that's going to be negative 18. And I'm going to divide both sides by 27. And, just be careful here, as always. You notice 27 doesn't go into there evenly, but it does reduce. Negative 18 27ths is negative, and 9 goes into both of those. So when I divide each number by 9, it reduces to negative 2/3. That is the y-coordinate of the point where these two lines would intersect. So I've got the y-coordinate, but to solve a system, you need to find the x and y values. Right? You need to find that point where they intersect. So now I just need to find the x value. And to do that, I'm going to take this negative 2/3 and plug it into one of the two equations. It does not matter which one, because it should be the same on either one. They should intersect at that one spot. But I will say, which one would it be easier to plug into? Either the first one or the second one? I like to go into that one where the variable was already isolated. So that one, x equals 3y plus 9, because if you take that and plug it in here, the x is already solved for. You can just replace the y with negative 2/3, and then just simplify on the right side, and you've already solved for x. But it's fine if you plug it into the first one in place of y. You'll get the same answer. So 3 times negative 2/3, right? That's going to leave me with negative 2 plus 9, and negative 2 plus 9 is 7. So that's what we're dealing with there. If you want to answer with an ordered pair, that means they would intersect at 7, comma, negative 2/3. And you still could graph these if you wanted. Put them both slope-intercept form, draw their graphs, and you should see they intersect right around 7, negative 2/3. It might be hard to tell, you know, the y-coordinate being exactly negative 2/3, but you should be able to tell it's between 0 and negative 1. And so feel free to still use those old methods. Okay, let's just try one more here, see if you get the hang of it. We're going to solve this one. 2x plus y equals 3, and 4x minus 3y equals negative 59. So the thing here, I said it's great to use substitution when you have one variable that is isolated, which I don't have. If you look here, in both equations, there's no variable that's totally by itself. But I did say either a variable that's isolated already or would be very easy to isolate. So if you look at that first equation, because that's just 2x plus y, see that the coefficient of y is positive 1, it would be very easy to get that y by itself by just subtracting 2x from each side. So I'm just going to pull this over to the side, and you know, if you can do some of these moves in your head, that's totally fine. Just don't make any careless mistakes. But just by subtracting 2x from both sides, I've just isolated y very easily just by moving that over there. And it should be said that you could use substitution by isolating either variable in either equation. It's just if you were to isolate x, for example, in this equation, you'd have to subtract y and then divide by 2, and then you're going to get some fractions. And it's not that you can't deal with fractions, but it just makes things a little messier. So this is my goal, is to try to avoid them. So I've got y all by itself now, and y is equal to negative 2x plus 3. So I'm going to go to the other equation, the one I haven't used yet, and that would be the second one in this case. And where I see y, I'm going to replace that with negative 2x plus 3. So the rest of the equation, exactly the same. 4x minus 3, use a set of parentheses in place of that y, equals negative 59. And now in place of that y, I'm putting negative 2x plus 3, because that's what y is equal to, right? Just taking this and basically substituting it right there. That's why it's called substitution. All right, now let's just use some algebra here. Watch your distributive property. We're distributing negative 3 to that group, so watch your signs. Negative 3 times negative 2x, positive 6x. Negative 3 times positive 3, negative 9, equals negative 59. Combine your like terms here. 4x and 6x is 10x. While I'm at it, I'm going to add 9 to the other side. Negative 59 plus 9 is negative 50. And now solve for x by dividing by 10. See, when it's down to one equation with only one variable, then I can solve that very easily. And I got x is equal to negative 5. And now I've got to plug that into one of my equations, and it does not matter where. And here's the thing, you can plug it into one of the originals for x. You know, I could put it in this first one for x, negative 5, or I could go to the second one and put negative 5 for x there and solve for the y. Or, like we did in the last problem, you can go to that equation where the y was isolated. That's a perfectly valid equation we use to solve here. So I'm going to, plug it into right here where y is already all by itself, because then I can plug it into that right side and just simplify. Negative 2 times negative 5 is 10. Positive 10, that is, plus 3. And 10 plus 3, you get 13. And there's our x and y values. So if you were to graph these, you would see that these two lines intersect at the point negative 5, 13. And there we go. Two different examples there of using substitution to solve a system of equations. Got any questions? Let me know. Otherwise, have a good day.